Hello students, hope everything is going well with all of you. So today we start a pretty dense topic, as if the sequences and summation notation and all that wasn't challenging. This is definitely going to stretch your boundaries and your comfort zone with math, but please be patient, right? Everything delayed gratification. Doesn't all have to make sense at first. Just try to struggle with it, stay through, right? Stay the course, as it were. And remember, this level of technical math is in BC calculus, and then it's in HL math, and then it's in differential equations and multivariable, because the degrees and majors where this kind of math is required are very technical. So if you're in this course because of your interest, but think, don't think I'm going the engineering, computer science route, if this piece of the mathematics really messes with you, struggle through it, because there's something to be said about struggling through something and managing to get through it, even though you know or don't think you may ever have to use it. But don't let it knock your confidence in math. When this stuff becomes confusing or you don't understand it, is not an indication that you're not good at math. It's an indication that this part of hard mathematics is hard. Okay? So, that being said, if you want to pause and do this warm-up on your own, or if you want to go ahead and just watch it with me, hopefully with some exposure to the summation notation here, this capital sigma, you understand that you're looking at the rule or the pattern, right? This is the rule for the sequence. And the sequence is being turned into a series because this notation, summation, says you are supposed to sum all the terms of the sequence, which means you've turned your sequence into a series. So hopefully you recognize this as arithmetic, which means you need the sum formula of the first 15 terms of an arithmetic sequence, and that formula is n over 2 times the quantity of the sum of the first term and the last term. So for us, we can fill in already our 15, right? And you can fill in your first term by, you're told to start at 1, so you're going to put 1 here. 1 minus 1 is 0, times 5 is 0, plus 2 is 2. And then your last term is you're going to put 15 here. So you're going to get 5 times 14. I'm sorry, 15 minus, 5 times 14, because 15 minus 1 is 14. And you're going to get 72. And you're going to plug this all into your calculator and get 555. The next one is a little annoying, right? Because they haven't given me, I have to figure out the rule. So I have to look at this and say, is this a common difference or a common ratio? Right, I'm not sure. So 6 minus 10 is negative 4, and of course 6 over 10, right, is 3/5. So now I have to go to the only other two terms that I have and compare, and I hope you can see that negative 42 over negative 38 isn't going to be 3/5, so this is not geometric. But the common difference, negative 42 minus negative 48, is negative 4. So this is arithmetic. So I need to use the same formula I did up above, S sub n. Uh-oh, I already have a problem, don't I? So in this case, what can I put in? Well, here I can, well, I should have in white put the 2, right? The 2 is always there. I can put in the first term, and I can put in the last term, but what I don't know this time is the n, right? So you have to use you have to write your rule. That's why you like summation. The rule is already there. You have to write your rule. Now it's not so bad, right? A sub n is equal to the first term plus, but in this case my d is negative, so minus 4n minus 1. And then I have to put 42 in here. And again, I'm not going to go through all of this because this was an objective from before, but you solve for n and you're going to get 14. So you do 7 times negative 32, and I got negative 224 when I was done. So again, look here. I like the fact that I've got my rule because I can right away see what my rule is. I recognize it's geometric. I recognize that my r is 3/4. And the absolute value of 3/4 we learned is less than 1. Therefore, the infinite sum, I'm sorry. Whoops, I'm getting ahead of myself. That's today's lesson. Sorry, I learned that r is equal to 3/4, so the sum of the first 20 terms is my first term. Now be careful, your first term is starting when k is equal to 0, so I don't care to the 0 power is 1, so my first term is 0 times the fraction with 1 minus my r, and then here 1 minus my r to n, and my r was 3/4. And you're just going to put this into your calculator, and I got a long decimal excuse me, that I put 3 places past the decimal. Okay? So I did want to show you a little bit on your calculator now. And the sad thing is that my online calculator, and there are better ones, but just the one that I have on my computer, isn't an 84. So the first thing I want to show you is just looking at a graph, and I've told you kind of already, I've hinted at the graphical relationships between these. If you put your calculator in the sequence mode, and then look at what I've put into, when I go to y equals, my y equals screen looks kind of crazy, it looks kind of wonky. The default is to start the n minimum at 1, and then I put the sequence rule in here. And then look at my window, right? My index is starting at 1. I stopped my index at 20, even though I wanted to go to 15, right? But I made it go a little bit past. And then look at my X min and max. That's my window. I wanted my window to go right farther. And I made my Y max go to 100. And look what happens when I push graph. Oh, snap. Those are the terms of the sequence. Look what happens when I push N. The first term, right, is when I plug in 1 and I got 2. So I could always use this, right, if I wasn't sure what my last term was. right? Remember I just plugged it in, I had a 72. Right now, of course, I could just use the formula and plug in the 15 as I did, but here's a nice way to see. And as you can see, remember I told you that arithmetic sequences, there is a linear relationship, right? Where your common difference is like your slope, your constant rate of change. So with a positive difference, you're going to end up with this sequence that looks linear. With a negative difference, it's still going to look linear, but just the terms will decrease forever, right? Look what happens when I change my rule to 2 times whoops, gosh darn it. What the heck? Where are they? Oh, remember my window, and remember R is less than 1, so my numbers are getting really, really small. So sure, I might want to go out this far, but I need to make my Y minimum. How about I make my Y maximum not 100, but just 1? Oh, there they are. 1.5. As the number of terms increase, right, the value of the terms gets smaller and smaller and smaller, right? So hopefully you can see these terms are going to 0 and just getting infinitely smaller, right? That's a really important concept going farther as we go into what we want to talk about today. All right, so that was a review of what we did. Now we're going to move to infinite series, right? Bit of a right mind-boggling concept. Infinite series. What the heck does that even mean, right? So in infinite series, remember that you are talking about adding, right? A series means you're adding terms. So like if you think about that picture that I just had, right, on the graph, that was a picture of the terms, not the sum, right? So this means we are adding to infinity or for infinity, forever. What the heck? So there's what this looks like in summation notation, right? So here is a sequence. So here is your sequence rule, your sequence pattern. There's my sequence. This notation, capital sigma, means to add the terms of your sequence, which of course then turns your sequence into a series. But I'm not adding the first 20 or the first 15 or whatever. I am adding forever. So here is the theory behind this. Don't worry, don't freak, right? Just be calm. If the sequence of partial sums, so partial sums means the sum of the first 10, or the sum of the first 15, or even the sum of the first 1 gazillion. Those are all partial sums, means that you stop somewhere. If the sequence of partial sums converges, so not the sequence of the terms, these, if the values, if this sum is equal to a number, and this sum is equal to another number, and this sum is equal to a number, if the sequence of the sums approaches a number, then the infinite sum is that number. Oh, my Lanta, that sounds so confusing. I know. This is going to make it worse. So, let's factor this. If an infinite sum of a sequence, which is a limit, right? A limit, because you can't really add forever. But if the limit as the n goes to infinity of the partial sums is a number, in other words, it is not an infinity, because we've done limits that go to infinity. If your limit of the sums, s sub 10, s sub 15, s sub 1,000, s sub 5,000, s sub 1 million, if the limit of those sums, if you make a sequence out of those summations, what do those summations, finite sums, approach? If it's not infinity, and it's not a does not exist, instead you get a number, then the infinite series converges to that number. If the limit does not exist, or is an infinity, because infinity is not a number, then we say the series diverges. For reasons that are not clear, and they won't be clear now, and they won't even be clear when we do this again in calculus, convergent series is what we're after. We love convergent series. If a series is divergent, our heart is broken, and we toss that series to the side. We're done with it. But if you have a convergent series, math is able to continue. You're able to do things with convergent series. The applications of these truly are so far beyond any high school class. Even when you do this in differential equations, it's still, the applications of the math even that you're doing in differential equations is beyond what a high school course is. But I can tell you, your cell phone doesn't work without convergent series. GPS doesn't work without convergent series. It's all in those communications, right? Your satellites, the drone going off and sending video back. That video doesn't, that communication from your remote, from your drone, doesn't work without convergent series. It goes a lot to programming and even into gaming, which is kind of crazy, right? Nothing that you're going to be able to truly grasp in a sophomore high school math class. But it is enough for you to know that what we want is a convergent series. So we want to be able to tell if a series diverges so we can throw it away. Okay? So I would really like to know when a series converges. So a geometric series will converge. I'm just giving you a fact. Write this down. If you've got a geometric series, and that's why we studied geometric sequences and then geometric series first. A geometric series, the sum of an infinite geometric series, will converge if and only if you find the common ratio, which of course you would have to know, given to know that it's geometric. Take its absolute value, and if that common ratio is less than 1, the geometric series will converge. The next statement is going to come above this, and you're going to wonder why I made my PowerPoint this way. Why did I tell you this first and this second? Both of them are series that you know. We've been studying geometric series and sequences, arithmetic series and sequences. Remember, I told you that what we want is convergence. Divergence breaks our hearts. So, arithmetic series, they're great. I know what they are. I can compute a finite sum, but you can never give me an infinite sum of an arithmetic sequence. So I'm going to go off on a little bit of a tangent here for a sec. And I'm going to do something silly. Here's how I think of convergent and divergent. There's a door. These are windows of a house. Here's the roof of a house. Now, remember, a series means you're summing. So I want you to think of a sum and I'm going to put the sum, I'm going to layer the sum in the house. So let's say I have a sum and I'm going to keep adding 5. So I started with 5 in my house and then I added 5 more. And then I added 5 more. And then I added 5 more. And I kept adding and adding and adding and laying these sums in my house, right? Add 5, 5, 10, 15, 20, 25, 30, right? And I kept adding 5 every time, summing as I went along, right? 5 plus 10 is 15, right? I took the terms of a sequence and I just kept adding and adding and adding. You know what's going to happen? I'm going to bust through the roof. I'm going to bust out of the house. Remember, if we say a series does not converge, we call that divergent. Arithmetic series are divergent because when you pile the sums on top of one another, the sum grows without bound. And I want you to think of not the series graph, right? If you just think about the linear relationship of the terms, I don't care whether those terms are positive, right? The sum of the first term plus the second term plus the third term plus the fourth term, this is all going to keep going and going and going. The limit, right? The limit goes to infinity. You're going to bust out the ceiling. As opposed to another series in a different house Here's a different house. This time, what's kind of crazy is if you pile, you keep adding and adding and adding values, but the numbers you're adding are getting smaller and smaller and smaller and smaller and smaller and smaller and smaller. I'm getting so, think about that graph, right? My values I'm adding are getting so infinitesimally small, you will